So, welcome back friends to another lecture on quantum field theory and quantum entanglement. So, we are looking at Dirac particles. So far we have looked at scalars and everything, and in the last two lectures we are looking at Dirac particles essentially. And the way we are proceeding Dirac particles is starting from the Lorentz transformations, and then we did not show the details about the Lorentz transformations, but we did not show the details how the Lorentz group is formed, but we showed that there is this Lorentz group because Lorentz transformations form a group. This group means it satisfies all the group axioms which we know, that it is closure, identity, associativity and existence of inverse. So, it forms a group, and this group is a continuous group, which essentially means that every the parameters of the group are essentially continuous, and it starts from unity, and such type of continuous groups are called Lie groups essentially. So, these are very special kinds of groups which are called Lie groups, and the Lorentz group forms such a Lie group with 6 generators. So, and these 6 generators are represented by a group which is called a special orthogonal group of 3 and 1 dimensions. Okay, it is not an SO4 group, but it is a special orthogonal because the metric which it leaves invariant is x square x t t square minus x bar square essentially. So, ct square minus x bar square. So, there is a minus sign. It is not like Euclidean metrics like x1 square plus x2 square plus x3 square plus x4 square essentially. So, to distinguish the line element from the other cases, so we want to say that the group associated with the Lorentz transformation is SO31. Okay. So, just to recap the Lorentz transformations form a group which is continuous, just like rotation group essentially, and starts from unity, it is special orthogonal. So, it is group of all Lorentz transformation are orthogonal essentially. So, it satisfies all the group axioms, the group axioms being so closure, associativity, identity, inverse, and the group has a name, it is called SO31. It is a special orthogonal group in 4 dimensions, but it leaves the metric x mu invariant x mu. Okay. So, this is what we mentioned essentially, but I went it through very fast assuming that you all are these are prerequisites sort of for this course. So, I assumed that you would know it, but I am just mentioning it. Go back, and if you do not remember, meaning do not understand these things, go back and study these particular aspects very well essentially. From this we move to the representations of the Lorentz group, and from the representations of the Lorentz group, Clifford algebra which we defined as the algebra of the gamma matrices, and we showed that S mu nu is essentially the commutator of the gamma matrices, forms a representation or satisfies the same Lie algebra, meaning that means the same commutation relations as M0 1 I and Mij, which are represent Lorentz group algebra as group Lie algebra. okay, satisfies the same. From there we can say that the vector space spanned by gamma matrices forms a representation of the Lorentz group. So, the vector space is nothing but the spinors. Okay, these are the spinors psi. Okay, spinors, which are mathematical objects which are called spinors, and these spinors form a representation of the Lorentz group. That means they are also particles which transform under Lorentz group. So, all the particles. So, the reason why we are trying to understand in this way is in modern quantum field theory. All particles in nature arise as representations of the Poincare group, which is nothing but Lorentz group. So, Poincare group is equal to Lorentz group plus translations. So, translations means what essentially? So, translations means Lorentz group I have shown you that it is this lambda mu. Translations are nothing but moving like this essentially, a mu, a mu. So, that means that x mu prime is equal to x mu plus a mu. So, you shift it with the distances. This is nothing but translations. So, the generators of translations are nothing but are p mu. So, that means p mu is a momentum essentially, 4 momenta essentially. So, the Poincare group has generators which are m0I, mij and p mu. This is the Poincare group essentially. M0I and mij are nothing but your lambda mu nu generators, and p mu is the generator of translations. Okay, Poincare group generators essentially. So, that is the reason why we went in this particular fashion. We started with so after the scalars were trivial because they transform just like scalars under Lorentz group. So, we did the scalar theory, we did all the things essentially. The next one we are looking what are other particles which can transform essentially under the Lorentz group, and one example is the Clifford algebra, which forms a representation of the Lorentz group. Now, what particles it represents and everything, we know the answer, but anyway we just act as though that we do not know, but let us just say that we know the answer that it is spin half particles, but how do we show that if we go by this logic, how do we show that it is a representation of the Lorentz group? If you start with the idea that all particles are representations of Lorentz group, then how do we know that you can form Lagrangians of it and derive the Dirac and the equation of motion and find the solutions of it essentially. That is a basic idea. So, along the way we formed the spinors. Essentially we looked at the spinors, which are nothing but the vector space spans by the gamma matrices. So, the spinors are nothing but psi 1, psi 2, psi 3, and then we looked at the bilinear covariants, spinors and bilinear covariants are so piners are essentially psi 1, psi 1, psi 2, these are complex numbers in this particular fashion essentially, and bilinear covariants are covariant quantities. Covariant means they transform in a covariant fashion. We have shown this essentially covariant quantities under the Lorentz group, which we have seen essentially. So, the all possible Guy-Linears are essentially scalar, vector, tensor and so on. So, okay, and then there are the actual versions of it essentially are covariant quantities under the Lorentz group. Okay, good. So, given this, I want to write the action. So, the Dirac action. So, I am already calling it as the Dirac action. So, the Dirac action is the action which you want to write from these points. Essentially, how will you write from these particles, which are the Clifford algebra representation of the Dirac of the Lorentz group essentially. So, how do you write the Dirac equation? The Dirac action or the Lagrangian is nothing but the action always should be real. The conditions on the action are should be Lorentz scalar real, okay, and it should be Hermitian and also okay Hermitian, and once we do interactions we will also put in other additional conditions like locality and everything, okay, but right now essentially let us just assume that it should be real and Lorentz scalar essentially. Now, with under these bilinear covariants, what are the scalars which are invariant under the meaning which are scalars. So, the only thing which we have are the scalars, and the other one which we can form a scalar is from the vector bilinear. Okay, we let us stick to only two things. So, let us try to write the action for the Dirac spinors. Action for the Dirac spinors. So, let me just remove this. So, it is obvious that it is already Hermitian. Okay, Lorentz scalar and reality. Okay. So, suppose if I write the first one I can write is psi bar I gamma mu del mu minus m psi. So, this is the Lagrangian, then the action is equal to d power 4x and this d 4x psi of x essentially. So, now you see how did I write the Dirac action. So, I have taken the bilinear covariant lambda mu psi, the vectorial current, and put a del mu with it. I put a combined it with a del mu. So, this gives me this forms a scalar, a Lorentz scalar, okay, and I put an I in front because it makes it real. So, I makes it real. So, if you put an I makes it real. So, the action is this part, the first term of the action is real, which is nothing but taking the vectorial current and adding a del mu essentially. So, these two are sufficient, this is one term. The second term I can write, if the particle has a mass, I can write psi bar psi then m. This I will tell you why this also psi bar psi also forms a scalar. I need to add an m in front of it, I will tell you why essentially forms a scalar as we have seen. So, what I mean by it forms a Lorentz scalar essentially. Now, this is action. Now you can ask why I don't put tensor, why I don't put, keep those questions for you, okay. I will answer them in due course essentially. So, suppose if I put tensor, I can write two derivatives, and then you will realize that the equation of motion will have higher and higher derivatives essentially, and such a thing is not good, okay. So, for the present let us stick to this one essentially, and then you will see, otherwise you will see some complications if you have more derivatives and everything. So, let us stick to vector and the scalar. Now, let us look at, the action should be real, and third one, it should be dimensionless. So, in h cross is equal to 1 units. In the natural units, it should be dimensionless. So, you have this action. So, S Dirac. So, let us do the counting essentially is equal to integral d power 4x and psi bar I del slash minus m psi. What is del slash? Where del slash is nothing but del mu gamma mu. Okay. So, del mu gamma mu, I write it in a combined fashion as del slash. So, your Dirac equation becomes much smaller and cute, and this you can, Dirac action becomes like this. Now, let us count the dimensions. So, the action should be dimensionless. So, d power 4x has in these units of mass dimensions m power minus 4, okay, mass dimensions power minus 4 essentially. So, that means this entire Lagrangian curly L Lagrangian density. So, the Lagrangian density should contain should go as dimension of the Lagrangian density should go as mass power 4. So, in this case you have the first things which are obvious is essentially the derivative. Del has mass dimension m is equal to 1, okay, it has a mass dimension m is equal to 1, okay. So, the first term psi bar I del mu gamma mu psi, gamma has no mass dimensions, should be having a total of m power 4, okay. So, this is clear, I guess, that this implies that the Lagrangian density should be of mass dimension 4, so that the total action should be dimensionless, and the derivative x mu should be dimension 1, which is obvious because x mu del by del x mu goes as a vector, and okay, x mu is mass dimension 1 essentially because lengths, and go as g power g say in h cross is equal to c is equal to 1 unit, go as mass dimension 1. The inverse the lengths go as mass dimension minus 1, and dels go as mass dimension 1 because they are the inverse of the lengths essentially. So, okay. So, with this the dels go as mass dimension 1. With this you have this particular combination, the first combination m should be for 4. Given that if you remove the del, this would imply that the combination psi bar psi should go as mass dimension 3. So, psi has a mass dimension m power mass dimension 3 by 2. So, the psi has a mass dimension 3 by 2 essentially, that is the basic thing. So, the Dirac equation has a mass dimension, the Dirac spinor has a mass dimension 3 halves essentially. Spinor has a mass dimension 3 half. So, now you see why psi bar psi has a mass dimension 3. So, you can put a mass term implies m psi bar psi in the Lagrangian. So, that is the reason why the mass will come mass term. In Lagrange. So, this leads to the mass term in the Lagrangian essentially with a coefficient m, and this m has also mass dimension 1 essentially, obviously, because sorry, this m also has mass dimension 1, obviously it should have mass dimension 1. Okay. This gives you the full dimension of the Lagrangian. From these dimensions we have seen that psi will have a mass dimension 3 by 2, and that is how it gives you this Lagrangian essentially. So, given this Lagrangian, okay, given this Lagrangian, so this is L Dirac essentially, which is nothing but psi bar I del slash minus m psi. Given this direction, we can derive, one can derive the equations of motion for psi bar as well as for psi. So, if you derive it for psi, okay, this will lead to, so it leaves, suppose if you vary with respect to psi bar, it is obvious that it leads to the fantastic I del slash minus m psi is equal to 0. This is the first equation of motion which you can get. This is the famous Dirac equation which many of you are familiar already. Okay. So, this is the Dirac equation. But we are in quantum field theory class, so we are doing it in a different way compared to what we did in the say for example, relativistic quantum mechanics lecture courses essentially. So, you do the same thing varying with respect to psi. So, psi bar, okay, psi, you get the conjugate equation which is nothing but I del mu psi bar gamma mu plus m psi bar is equal to 0. This is the Dirac equation for the conjugate psi bar field essentially. So, this is the Dirac equation for the psi bar field. Okay. So, you have these two beautiful Dirac equations, okay, and okay. Now, it is still first order. Of course, there are these very fantastic interesting properties, some properties of the Dirac equation which I will just mention essentially, that a few things, that it is first order in the Dirac equation is first order in derivatives, and it does not it's still, of course it is still Lorentz invariant. Okay, and then okay, we'll also see how to okay, it is first order in derivatives essentially, and it's still Lorentz invariant. Obviously it will look like okay. Now the point is that we can, there is another property, say for example take the Dirac equation and mod it with another del mu, the opposite one, okay. Psi that is equal to minus gamma mu gamma nu del mu del nu plus m square psi of 0, okay. So, but this is nothing but gamma mu gamma nu del mu del nu is equal to half gamma mu gamma nu del mu del nu, that is nothing but del mu del mu. So, essentially what we get is the equation so this is a familiar equation from the scalar field theory. So, this is nothing but the Klein-Gordon equation. Okay. Now, this does not have okay, let me just clarify a little bit more essentially. So, this okay, this is the Klein-Gordon equation. Now, okay, before going, okay, now, okay, just a few more things of the Dirac equation. So, I will come back to this means, okay, okay, now I will come back to this in a second, but let us see this one, I del slash minus m psi. This is actually a matrix equation. This is equivalent to I gamma mu del mu minus m times psi is equal to 0. So, this is equivalent to I gamma 0 del 0 minus gamma I del I minus m whole thing into psi is equal to 0. Now, this is equivalent to minus I. Now, gamma 0 and gamma I have already mentioned what they are. They are these 2 by 2 matrices. Okay, this is okay, gamma 0 into del 0, and gamma I also mentioned 0 sigma I think del I minus m into del I minus m whole into psi. So, essentially this is a 4 by 4 matrix equation which is coupled essentially, matrix equation coupled essentially, coupled matrix equation. So, this is essentially you have gamma 0 del 0, okay, del 0 essentially. So, del 0 minus so you have, so this entire format is a okay, I think you can write it down explicitly. It is instructed to write it down completely. You have derivatives in the diagonal, and you have derivatives also in the off diagonal. Essentially you have, there are time derivatives and the off diagonal and sigma derivatives with respect to what you call essentially this. So, there is day 0, there is sigma I del I, sigma I del I. So, you have a form like this. Now, if you expand the sigma matrices also, it is a complete 4 by 4 matrix, and so you have the space derivatives in the off direction and this in the full direction, and then you see that it is a complicated 4 by 4 matrix equation which is coupled, and this is because of this matrix equation. So, it is instructive, I expect it is instructive to write down the full 4 by 4 matrix equation of the Dirac equation. See, so this simple notation, it looks so simple and very discerning, which looks very easy and charming, but it is actually a complicated equation. So, it is a complicated equation with 4 by 4 matrix multiplying a complicated, and there is also an m sitting here, essentially there is an m, okay, in the time direction, okay, in the diagonal form, okay. So, there is also an m sitting here, and this entire thing is a complicated matrix equation. So, it is instructive to write it down completely and now, and check what is the exact form essentially. These sigmas are not looking so nice essentially anyway. So, you can work it out and write it down. I would suggest everybody of you, and if somebody of you have already taken the relativistic quantum mechanics course or the quantum mechanics, you would have done it already, meaning you have done it in great detail. Now, the point is that now if you see this equation, the square of the Dirac equation, or which we call as the Dirac equation, which I operated this particular factor again on the Dirac equation, I consider, okay. So, this is called, this trick is called the square of the Dirac equation is the Klein-Gordon equation. So, this is the trick in which you take this operator, multiply it to the Dirac operator, and then you see that this is just a conjugate, meaning the plus sign of the Dirac operator, and you see that it gives you back the Klein-Gordon equation, but the resulting thing is completely diagonal. That means there are no gamma matrices. There is no this complication due to the gamma matrices. So, this Klein-Gordon equation acts on every component of the Dirac equation. So, every component of the Dirac equation satisfies the Klein-Gordon equation. So, this you see, so del square sum square. So, acts on all of these operators, all of these components psi 1, psi 2, psi 3, psi 4 is equal to 0. So, every component of the Dirac equation satisfies the Klein-Gordon equation. This is the important thing. Okay. Okay. So each component is like a scalar field. Each component of the Dirac equation is like a scalar field. Okay, good. Now we will move to the solutions. So, before moving to the solutions, let me take a break. Essentially, I will stop here, and then we will come back while doing the solutions. Okay. Okay, good. So, what we have done today is essentially looked at how to write the Dirac equation, Dirac action. How did we get the Dirac action? So, all we have done, see, in the entire exercise today, we have done it completely differently. We started with the Lorentz group representations, and then we wrote down the Dirac action, and from the Dirac action, we derived the Dirac equation. Meanwhile, we fixed the dimensions of the Dirac field to be about 3 halves essentially in 4 dimensions, and then we looked at we have started looking at some properties of the Dirac equation, like for example, we looked at it's in first order in derivatives. Then we said that the square of the Dirac equation should give me back your Klein-Gordon equation, and then the Dirac equation itself is a complicated equation which is a 4 by 4 matrix essentially. Now, we will stop here and then we will move further. We will now look at solutions of the Dirac equation and a little bit more, because completeness relations, orthogonality relations, these are important, because at the end of the day when we have to do the derivatives we would need these, we have to know the propagators, we would need this, and we have to calculate cross sections. These will be very important essentially. Okay. So, let me stop here. Thank you very much actually. Yeah.